Another type of diode circuit that I want to briefly introduce is a clipper circuit. And so as the name suggests, what a clipper circuit does is it clips portions of a signal that are either above some threshold or below some other threshold. So you'll also see these circuits called limiter circuits, and so the reason for that is, of course, we can use these to limit the voltage seen by sensitive electronic components. So let's take a look at what our circuit looks like. So here's an example of a clipper circuit, and so let's assume that we have some sinusoidal input for our VI. So I've already got a sort of rough sinusoidal signal drawn here, so that's our VI in blue. And so just sort of qualitatively, we can think about what's going to happen. As we have really large values, so as we get into these peak values, we're going to have a positive voltage up here on the top. And so what that positive voltage is going to do is it's going to forward bias our diode D1. So that means we're going to have a V gamma voltage across V1. And of course, our battery here, VB1, is just going to have that voltage there. Now, if we're using our piecewise linear model, and we assume that RF is equal to 0, what that means is that our output voltage is going to be fixed at this value of V gamma plus VB1. Because our reverse bias diode over here, our VD2, it doesn't have a fixed voltage across it. That voltage can vary a little bit. So if we come to draw our output curve, we can say as we get above some value V gamma plus VB1, we essentially have a fixed output at that value. So let me come in here and draw this V gamma plus VB1, and let's draw a dashed line across here to give us a good reference. So we have something that looks like that, and what we're saying is that if we come in here with, let's do green, if we come in here for our output is following this, but then once we get to this point, our diode D1 becomes forward biased, we have V gamma across it, and our output voltage is staying constant at V gamma plus VB1. Now keep in mind, this is assuming that RF is 0. If our RF is non-zero, of course we'll have some deviation to that, but if RF is small, then of course the deviation shouldn't be too large, which kind of depends on that resistor value, which we'll point out a few things about that in a little bit. Okay, so as that voltage drops below that V gamma plus VB1, it's going to start tracking with our input voltage again. But at a certain point, it's going to get really low. So down at these points down here, what we're going to see is that we have sort of the opposite case, where now this part is going to be really positive, and our diode D2 will be forward bias. Our D1 will be reverse bias, so it can have, essentially we can think about it as a larger range of voltages across it. It doesn't have to be fixed, whereas our V gamma is going to, or our VD2 is going to have a value of V gamma, again, assuming that we have RF equal to 0. And so again, we're going to have our voltage fixed. Now it's going to be V out is equal to negative V gamma minus VB2. Or we can write that a little differently. Let's again put another dashed line down here. Let's go ahead and put that here. So we have something like this, and what this value is this is going to be our negative V gamma plus VB2, or as I said before, minus V gamma minus VB2. And so let's come back here and continue this line that we were drawing. So we said it's going to track our input, but then once we get to this point here, that D2 becomes forward biased with a voltage of V gamma, so our output gets clipped above that point. Then we follow our input voltage up to this point, and then again it gets clipped as that D1 becomes forward bias, and so on and so forth. See if I can trace lines a little better. There we go, that's a little better at least, and then it gets clipped down here at the bottom part. So again, this is a good example of maybe we have some electronics over here on the right where our V out is indicated. So maybe we have something sensitive that we want to connect between here. And if we don't want it to see a voltage above, let's say 5 volts, we could incorporate a clipper circuit such that it doesn't get up to that 5 volt area. One thing to note is that these upper and lower thresholds do not have to be symmetrical. Of course, we could adjust the values by having different values of these batteries or these supplies. We could also have different diodes, and that could slightly adjust the value, but really we're going to get more variation from changing the battery's VB1 and VB2. One other note about that is instead of batteries, what we could do is we could replace those with Zener diodes. And so, of course, the benefit of that is we're not having to change batteries. We're not having to use a lot of energy. But remember, our Zener diodes are good at keeping a constant voltage. So we could have Zener diodes that are cutting on or cutting off depending on what part of our input waveform we're at. One other thing I wanted to point out too was related to this resistor up here. So what value should we have for this resistor? Well, we kind of have to consider a couple things. We want this resistor to be large enough such that we're limiting current in the forward bias case. We don't want to damage our diodes. So large enough to limit current in forward bias. So that's when our diodes are on. So we could think about that as these times here when one of our two diodes is conducting. However, we don't want it to be too large, but small enough so that we don't get a large voltage drop from our reverse current of our diode. So small enough such that reverse current of diodes doesn't cause a big drop. And so in that case, of course, what we would have is we would just be losing a lot of energy as we're dropping a large amount of voltage across that resistor. So again, it kind of depends on our specific application.